when the linear model has one predictor variable, then we've got two coefficients, the beta 0, which is the intercept, and the beta 1, which is the slope, which beta 1 we have to multiply by the predictor variable, and it will indicate the beta 1 indicates how much the outcome variable increases as a unit increase in the predictor variable. Okay, so we've got beta 1 and beta 0 and beta 1. These are the values that we are interested in, which are the coefficients. We call the coefficients of a regression, or the coefficients in a linear model, and we want to make an estimation of those values in the population. How do we do that? Exactly the same as before, but the probability demon will have to do two sampling distributions, one for beta 0 and one for beta 1. We start with the calculation of B0 and B1 in our sample, and we estimate, we make the assumption that in the population those values that we calculated in our sample will be the true values. So the B0 we calculated in our sample, that's our estimation for the best, the most probable value of beta 0. And when we calculate B1 in our sample, that's our best estimate of beta 1 in the population. And then the probability demon will do that the same as it did with when we had to estimate beta 0 only. So what did it do? It took a random sample from a population in which the value of beta 0 is the same as the B0 we calculated in our sample, and beta 1 is the same as the B1 we calculated in our sample. It has to have the same number of observations. So in the example of when we estimated the mean, then the probability demon calculated the mean of that sample. In this case, instead of calculating the mean of that sample, we calculate the B0 and B1 of that sample. And then those values return to the pool of the population of values, and the probability demon generates a new sample, random sample, and calculates the beta 0 and the beta 1, or the B0 and B1, and again and again and again 10,000 times. So now we've got 10,000 B0s, which are the estimate for beta 0, and that's why we call it beta 0 hat. And we've got 10,000 of B1s, which are estimates of beta 1. So that's why beta 1 hat. With those 10,000 values the probability demon generates a sampling distribution, and that sampling distribution will have the mean is the exact, as we did with the mean in the previous example, it will be exactly the same B0 and B1 we calculated in our sample. Now, that distribution will have a standard error. It's not a standard error of the mean anymore. It's a standard error of beta 0 estimate and standard error of beta 1 estimate in the other distribution. And based on this standard error, we apply the knowledge we have of normal distributions, in which 95% of the values are found between negative 1.96 and positive 1.96. So to calculate the lower bound of the 95% confidence interval, we do minus 1.96 times the standard error of beta 0 estimate, and that's the lower. And that we add to the mean, which is the beta 0 estimate, and that gives us the lower bound of the confidence interval. To calculate the upper bound of the confidence interval, we do 1.96 times the standard error of the estimate, and we add that value to the mean of the distribution, which is beta 0 estimate. And we do the same with a beta 1. Now, traditionally this is not done with the normal distribution, it's with the t-distribution, but is more is easier to explain with the normal distribution